Hello, everyone. Welcome to the Meet the Young Professional series talk, where we host the former members of the IEEE Bangladesh section who were once part of our section and then moved to different parts of the world for their career. And today, I'm glad to host our today's speaker, Dr. Imtiaz Ahmed, who's currently an assistant professor of computer science and engineering at Marshall University, West Virginia. If you kindly keep yourselves muted if you're not speaking. Thank you very much. So Dr. Imtiaz Ahmed has been an active member of the IEEE Bangladesh section. So he completed his, before completing his PhD, he was actually working as a faculty member in the Department of IEEE of Bangladesh University of Engineering and Technology. And while that, he was actually serving as the chair of IEEE Graduates of Last Decades, which is now renamed to IEEE Young Professionals. So he was actually a former chair of the Young Professionals. And he went to the University of British Columbia, Vancouver for his PhD in ECE. And now he's working at Marshall University, West Virginia, USA as an assistant professor in CSEE. And he's currently working in primarily in wireless communication. So we would like to know more about how his research is in the broad context and how it can benefit the young professionals and engineers of our country. So without further ado, I would like to invite Dr. Ahmed to share his talk with us. Thank you.
Okay, and so hello everyone. So Sajid, can you hear me? And
yes, we can hear you, and we can also see your slides.
Oh, okay, sure, perfect. Thank you so much, Sajid. So first of all, yeah, thanks a lot to Sajid and the IEEE Young Professionals Bangladesh. And first of all, let me welcome you in my presentation. Good evening to you all who are attending this presentation from Bangladesh, and good morning to myself and friends from US/Canada, if there is anyone here attending. So today's talk is entitled as Working in the Areas of Wireless Communications. And as Sajid mentions, my name is Imtiaz Ahmed. I'm working as an assistant professor in the Department of Computer Sciences and Electrical Engineering at Marshall University in Huntington, West Virginia, US. So before going into the main technical talk, let me briefly say a little bit about my background. I'm very new to academia. I just started my journey here at Marshall more than just 1 year ago. And before joining Marshall, I worked as a wireless systems engineer in Intel Corporation in San Diego, California for around 3 years. I completed my PhD from the University of British Columbia in beautiful Vancouver back in 2014. And then I briefly did 1 year of postdoc at McGill. I completed my undergrad and master's from BUET. I'm actually from 2000 batch from IEEE. After finishing my undergrad back in 2006, I worked there as a lecturer and then as an assistant professor until 2009 for around more than 2 years and a half. This is the high-level contents of my presentation. So at first, I will go over a few of the research works that I am currently involved with, a few topics, and I will try to explain or just give some sort of highlights of a few of the examples of the work that I'm working on. And then it will be followed by a very generic topic on how is like or how does it feel working as a research wireless communications engineer, either as a researcher or developer or validation engineer, roles of wireless engineers in the industry, and a few other general topics. So let's quickly jump into the technical details, and let me just say a few words what actually motivates me towards the research in wireless communications. So right now, we are in the like almost like the end part of the fourth generation of wireless communication systems. And in terms of wireless systems, I would like to confine myself towards the cellular communication standard, but the current almost like the end part of the current standard is the long-term evolution, or LTE. And we are almost like approaching to the next generation of cellular standard, which is the fifth generation of communications, or for 5G new radio NR. So LTE was initiated by the standardization organization 3GPP back in its release 8, and since then we saw LTE, LTE Advanced, LTE Advanced Pro, and so I mean, but we always want to move forward and want to achieve a much better performance. So that's why the researchers all over the world came forward to set a high level of standards for the next generation of communications, which is for 5G, where the data rate has to be few gigabits per second. The bandwidth has to be much more than what we have right now. The coverage has to be equally like equally enhanced compared to LTE. For one set of applications, the energy consumption has to be much lower than what we have. For another set of applications, the transmission reliability has to be extremely high, and the latency has to be low. So when we put all these requirements together, we can represent the features of the 5G in terms of a triangle, where on the top vertex we have enhanced mobile broadband service, which is nothing but some sort of like a straightforward extension from LTE to 5G NR. On the left side of the triangle, we have the massive IoT, massive Internet of Things. So IoT, right? We have like a bunch of different standardization techniques, and it also has a fair share of allocation in cellular communication standard, something we call narrowband IoT for LTE. But for massive IoT for 5G, it's going to be much comprehensive, and there will be much more coordination among multiple standards. And then on the right hand side, we have ultra reliable and low latency communications, where the transmission reliability has to be extremely high, and the latency has to be, or the transmission delay has to be very low, less than few milliseconds. A few notable examples of this sort of communications can be like autonomous driving, tactile communications for remote surgery, things like that. So there are like a bunch of ways to improve the system performance, and we can achieve these performance requirements. And from a very fundamental aspect, or from the physical layer aspect, can be as follows. Like, let's say we can always increase the transmission bandwidth, but there is some sort of like issues. Increasing transmission bandwidth is not a very straightforward approach because our licensed spectrum is quite limited. One approach can be toward going towards the very high range of the carrier frequencies of the electromagnetic spectrum, and can exploit the millimeter wave. But we also face some sort of issues, like the transmission path loss is really high. In order to encounter this problem, we can use many number of antennas at the base station, something we call massive MIMO, and it also brings a bunch of challenges that we need to tackle. We can also increase transmit power, but increasing transmit power not only not only puts a burden on the service provider, but also raises some sort of like an environmental concern. It can enhance the level of interference. One way to solve the environmental concern is to use the renewable energies, which is essentially a green energy supply. And then we can, in the physical layer, we usually have very strong and robust signal processing algorithm, but still we can deploy some very advanced techniques, very intelligent and data-driven processing, and we can push the boundary of the performance limit, or equally we can decrease the computational complexity. So I would like to discuss my current research work in different sectors. Like, I'm trying myself getting involved in different parts of wireless communications, like starting with the first the first solution that I just said, and sorry, the second solution that I just said, how we can exploit renewable energies for the purpose of wireless communications, and the application areas are precisely for the massive IoT for 5G. And the second one is employing some sort of like a very advanced signal processing technique for getting the solution of very fundamental problem like channel estimation and tracking, and specifically for millimeter wave 5G communications. And then the third one, artificial intelligence is right now booming, and wireless communication systems is not an exception. So I'm trying to get involved myself with developing some deploying the artificial intelligence tool, I should say, in the design problem. And the last one is how to use drones or unmanned aerial vehicle to provide the network, to provide some sort of like temporary network coverage, to enhance the network coverage for a macro cell network. But this brings a lot of challenges that we are working on to solve. So this is a mind map diagram of my current research in different sections of wireless communications. Let me give you some brief examples in each of the sections. Let me just start with the fundamental, the first one, how we can exploit renewable energies for the purpose of wireless communications. And in this context, we define a concept which is called energy harvesting. Energy harvesting, we specify this term as a particular node, and we call them as the energy harvesting nodes. They can capture, usually they can capture energies from the renewable sources and can convert them into some suitable format of the energy, can store the energy for future use. So collectively, a node that is capable of like conducting all these activities, we call them as energy harvesting nodes. And energies usually can be harvested in different renewable sources, like from solar, thermal, mechanical, vibration, or even from the radio frequency electromagnetic wave. And in this way, we can ensure that we can increase the system lifetime, and we can ensure a green energy supply. But the question to ourselves is renewable energy, energy harvesting, these are definitely not a new concept. So why doing research along this direction is interesting? That's a fundamental question that we need to get an answer for. So we would like to get the answer from the perspective of wireless communications. Usually, let's say that when we design any wireless communication systems, we assume that our energy supply is pretty much deterministic. So whether it's coming from a battery or whether it's coming from a power supply, it's kind of like a deterministic entity. But if we say that we are gonna power up the node with the energy harvesting concept or from the renewable energies, this energy is pretty much, or very much, I should say, random in time and random in amount. And in addition to that, based on the application areas, I just say that the application areas are precisely, let's say, for an IoT network, where we have a bunch of constraints in terms of like a form factor or in terms of like battery size. Sometimes we face some issues with the limited computational resources. And in many cases, when we design the problem, we need to solve some really complicated problem. So given the randomness of incoming energy, having some constraints on the form factor, the physical size with some limited computational resources, we strongly feel that this is a very, very challenging problem. And if we want to satisfy all these constraints. So that makes the problems really cool and interesting. And along this direction, there are like a bunch of ways to contribute to the wireless community, but I myself confine towards the resource allocation problem in wireless systems. So the question is, what is resource allocation? Wireless systems have a bunch of resources, like the energy supply is one of the resources, and then the number of antennas, then the channel. These are all resources that are essentially like allocated among the entities, or the utilities, and here the utilities are the users. So resource allocation is a very important and challenging problem sometimes in wireless systems. But one can simply argue that, okay, what's the big deal here? I mean, like just go for some heuristic algorithm, solve the problem, and we are done. Yeah, we are done, but we are engineers, so the best bet is always to solve this problem in a systematic manner. Usually what we do, we formulate an optimization problem with a specific objective function. Let's say that we want to maximize the end-to-end system throughput, or we want to minimize the cost, like the power. We have a set of constraints, like that the transmit power cannot be more than certain threshold, or we need to satisfy some quality of service constraints. And then obviously we have the optimization variables, which are none but our resources. So when we formulate an optimization problem, as long as we can represent every single quantity analytically, then we always try our best to solve this problem optimally and efficiently, and if possible, through some analytical equations, so that this gives us some sort of like a direction that, okay, we can design the problem, we can design the system, we can allocate the resources uh, following this approach, something like that. I'm going to show one example of resource allocation with energy harvesting nodes. Here is a typical system block diagram of a source, a destination, and number of relay nodes. Source wants to transmit some data bits to the destination, and it doesn't have a good forwarding channel to transmit to. So what it does, it tries to get some help from the relay nodes. And what the relay does, relays work in the decode and forward mode. They receive information from the source, decode and re-encode, and then transmit to the destination. This is not a very new problem. This is kind of like a very fundamental problem from the cooperative communication perspective. Like it was like really popular framework back in 2000, I would say 2011, 2012. But why is it still like this kind of problem interesting? Because here we make an assumption. We assume that our source and the nodes, they don't have the conventional power supply. They have some energy harvesting nodes. They can harvest energies from the renewable sources. And based on their harvested energy, they transmit data bits, or they do their signal processing task. And this incoming energy is a random variable. And also here, the channel between the source and the relay nodes, or from the relay to destination, they're obviously like modeled as a random variable. So here, what we want to do is we want to calculate what should be the optimal transmit power for the source. And at a given time, we select only one relay. Which relay should I select, and what should be its transmit power? Something that we need to compute, we need to calculate. And this, when we are saying that we want to calculate these things, this falls under the umbrella of a resource allocation problem. So what we did, we formulated an optimization problem, tried to solve the problem. One more assumptions that we made here, we state that the incoming energy and the channel are modeled as a random variable, and so they should follow some statistics, but we assume that this statistics is very time varying. We don't know exactly the statistics of this random process, which means we do not know their average value, their probability distribution function, and that make our problem even more complicated and even more practical. So what we did here, we applied some sort of like a learning technique, and at the same time we calculate the optimal transmit power, optimal selected relay through some reinforcement learning approach. So this is a typical formulation of an optimization problem, and then we uh, after like a long derivation, we came up with some sort of like an easy representation of this problem formulation, and so that we can right away apply the learning algorithm, because this is the Markov decision process. But I'm not going to go over all the details of the math, but just to give you some sort of like a glimpse that, okay, this is how we formulate an optimization problem, and we try to solve the problem, let's say here, for using some learning technique. And let me show some results. Let me express the outcome as an average throughput, which is bits per second per hertz, as a function of number of transmission time intervals intervals. And here, the curve that is shown in the magenta color is the performance of our proposed algorithm, and the blue one is an upper bound, a theoretical approach or upper bound of like end-to-end system throughput. And there are like a couple of other curves that are some sort of like naive approach, which do not show that much of good performance compared to the upper bound, but we would just try to make some comparison. Here, first of all, this curve, the curve that is presented in magenta color is the one that comes out of the learning algorithm that we proposed. And obviously, it performs much better than the other two naive algorithms, the red one and the gray one. But compared to the theoretical upper bound, for a small number of time intervals, there was a gap, there was a performance gap. But as the time progressed, then this gap shrinks down, and then we can say that our proposed algorithm is good enough to show the equal performance, some sort of like comparable performance of the theoretical upper bound. So the point that I'm trying to say or trying to make is, like, even for a complicated or very practical problem, if we can put some effort on breaking down the problem and getting some sort of help from some tools like reinforcement learning here, we can still achieve the same optimal performance as what would be offered by the optimal offline scheme. Along this direction, I have a few other problem sets that I'm currently working on and trying to collaborate with other colleagues. I'm right now more interested in developing some practical prototype for energy harvesting IoT module, which will give us some sort of like a practical flavor of how the system should work and perform. And then a few other works, like from the higher layer perspective, where for a distributed IoT network, how should we maintain the security or privacy with some like really cool advanced learning techniques like the federated learning, things like that. So let me jump into the next example that I would like to show, which is something for millimeter wave communications. Just to give you a reminder that the millimeter wave is something that we are going to adopt for 5G NR. And some of the fundamental problem that, like the channel estimation tracking, those were well established back in LTE. To some extent, they need to be revisited for 5G. And essentially, as we briefly mentioned, that for millimeter wave communications, we use many number of antennas at the base station, something we call massive MIMO. And in practical system, we try to use a uniform planar array of antenna to accommodate many number of antenna elements for massive MIMO, some sort of like an uniform planar array. But this actually makes our, let's say, channel estimation problem a little bit more complicated, because usually for LTE, let's say that if the antennas were like aligned in a single dimension, then we did not have to think too much about the details of the angle of arrival, angle of departure. But here, for uniform planar array, let's say when we jointly jointly estimate the channel parameters, we have to estimate the channel gain and angle of arrival, angle of departure. And just to give you an overview, the channel estimation is a fundamental approach for the data detection. So channel estimation plays a very important role, not only the channel gain, but some other parameters as well. So here we found out that this problem is quite interesting in the context of millimeter wave. So the first approach that we did here, we instead of directly jumping into the practical problem, at first we tried to get some theoretical bound of the estimation theory. That's something we borrowed from the Kramer-Rao lower bound. We derived a bound which actually gives us, okay, this is the maximum possible performance that can be achieved for a given configuration of antenna arrays. And then we actually develop some sort of like practical algorithm to do the channel estimation and channel tracking over time. So this is like a lot of maths behind this theory of the Kramer-Rao lower bound, but let me just quickly jump into a few of the results. So here we just want to show the performance of the estimation accuracy in terms of the mean squared error and the Bayesian CRLB as a function of number of pilots. So we use pilot symbols to do the channel estimation, and it's fundamental. And this the derived up lower bound that we just showed, we just discussed, gives us some sort of like how good the practical algorithm can be. So what is the maximum possible performance that we can achieve for channel estimation in millimeter wave? So the theoretical derivation that actually gives us this sort of like entity or this sort of direction. So here we show the performance, the error mean squared error performance. So the lower the error, the better the performance is. So here we showed the performance for two different configuration of pilots. And let's say for the blue colored performance here, the solid line shows the theoretical upper bound, theoretical lower bound, and the dashed line is one of the practical channel estimation technique that we proposed. And here just we are just showing this thing to just ensure that okay, if the performance of the dashed line is close enough to the solid line, then it looks good, it's better. But I mean, the our approach is always to go towards this solid line from the practical scheme, so that we can sell our like algorithm in a way that okay, this one is good enough for doing the channel estimation, which means that the joint estimation of channel and then angle of arrival, angle of departures in different planes. Along this direction, for millimeter wave, we have quite a few interesting topics that I mean, those are not, I'm saying that open problem, but there are some like few problems that we can still contribute along this direction, like some parameter estimation for the channel, like timing offset, like frequency offset, Doppler spread, and then also some sort of like beam estimation and tracking. So they are very challenging problems, and we still need to, although like there are like a lot of solutions out there, but still we have room for further exploration, exploitation. Next, I would like to say a few words in the artificial intelligence in physical and math layer. Right now, AI is simply booming. Wireless communications is not an exception. But what about from the physical layer perspective? Because in physical layer, when we talk about the digital signal processing, we already have very strong and very robust signal processing algorithm that are good enough. We don't want to reinvent the wheel by just replacing those techniques with the cool artificial intelligence tool like deep learning or machine learning, shallow learning, things like that. But we still feel there like enough room to do the contribution. First of all, usually for wireless communications, the algorithms that we develop are block based. Let's say that we come up with an algorithm that does the demodulation, or that does some sort of like decoding, channel coding. These are like block based. So for a given block, there are some optimal algorithm. But it was shown that if we just remove the boundary of the blocks and replace, let's say, 2 or 3 blocks with a deep neural network block, sometimes we can push the boundary of the end-to-end global optimality. Something where we can think of that, okay, the deep neural network will really be helpful to be used in those sort of problem solving those sort of use cases. And the second one is we can always go for reducing the computational complexity, and sometimes we can train things offline and apply them in online, and somehow we can reduce the online or real-time computational complexity. So I started with a very fundamental problem, like just a very fundamental problem, signal detection in different sorts of noise. So usually, let me just quickly jump into the system model. Say here we have one transmitter and one receiver, and the receiver is equipped with multiple antennas, and here transmitter transmits signals and the multiple copies are received at the receiver, and the receiver combines them. It increases signal to noise ratio, and then it helps us for improving the bit error rate performance. So usually the maximal ratio combining MRC is the optimal approach sorry is the optimal approach to combine the signals, given that the underlying noise is Gaussian distributed. But if somehow, in some cases, if there is a presence of non-Gaussian noise, there may be like impulsive noise or any sort of noise, that will make the problem a lot more complicated. So in even those scenarios, the maximal ratio combining does not perform optimally. It performs like suboptimally. And in those cases, one approach can be to derive an optimal maximum likelihood detector that will give us optimal solution. But we need to know the noise distribution. We need to develop the detection technique for a given noise, and it will make the problem a lot more complicated from the practical implementation perspective, given the form factor of the size of the phone, or maybe for some other receivers, it will be a lot more complicated. So that's why we thought that, okay, maybe let's just use a fully connected deep neural network and train these things, train this model with different noisy observation, and use this trained model, the real system, to detect the data bits. And interestingly, we found some really good results for different non-Gaussian noise. Here, we show the performance in terms of a bit error rate as a function of average signal to noise ratio for two different sets of noise. One is the blue colored one is another one is the red one. So for the blue colored one, the solid line shows the bit error rate performance for the maximal ratio combining for a given non-Gaussian noise, and obviously this does not show the optimal performance because its counterpart, the dashed line, is the bit error rate for the receiver where we use the deep neural network. So obviously for a given signal to noise ratio, the bit error rate for the deep neural network is much lower than what we see for the for maximal ratio combining or the well-known detector. And we also compared the bit error rate performance of the deep neural network with the optimal maximum likelihood case. And interestingly, they show the same results, which really like excites us that, okay, we can use deep neural network to detect non-Gaussian, to detect symbols for different non-Gaussian noisy environment, and that really gives some cool results compared to the conventional technique. Along this direction, we have a number of problems at hand. I'm collaborating with a few other faculty members and in different universities or in US and Canada, for example, like the pre-coded design, MIMO signal detection, and different other problem sets. So the last topic along this section is how the UAVs or unmanned aerial vehicle or drones can assist in communication. So usually, like it has been, it's also going to be, it's also like included in the standardization that UAVs can provide some on-demand and infrastructureless support, especially in the time of disaster, and then they can work as a mobile base station or relay. But still, a lot of research needs to be conducted, and some of the fundamental problems need to be revisited. Let's say that when we develop a wireless channel model for UAV network, we have two different types of things, like air to ground and air to air. And so that's something I'm right now working on, and this is a practical task that I am currently mostly involved here in my university. And we have practical prototype, and that's something where we are doing the channel sounding based on the software defined radio, and obviously with the drone. So a few setups, like we are using just a fundamental software defined radios that can work like up to a few gigahertz range, and then I mean, like for doing the communication part, like we are using the Raspberry Pi, we're connecting it up with the drones, and we have a ground station, and then we are taking the measurement in different parts of the city to see the channel gain, and then the delay, and then the Doppler spread, things like that. So this project is quite new, and we just started, and we have a long way to go. And few other open problems like the three-dimensional placement of the drones, optimal location tracking, and then few problem sets from the higher layer of communications, like deriving some routing algorithm for drone network, is something that we are also working on. So given having said all this like technical things, now this talk is dedicated for IEEE young professionals in Bangladesh. So I would just like to discuss something very, very general. So for example, like, how does it feel like working in the areas of wireless communications, and the roles of wireless engineers in different parts of the industry. And then what would I do if I could travel back to my early 20s? Some advice to myself first, and then to others. So first of all, obviously, communication engineers can work in academia and obviously in industry, in different roles in the industry. And but I just stepped in academia. I don't dare to talk much about it right now. Maybe in 4 to 5 years down the line. So let me say a few words on the industrial works in the areas of wireless communication. So before discussing further, let me just put a disclaimer here. Whatever I will say is entirely from my own perspective, from my own point of view, and others may have the same, others may observe the same thing, but from a different angle, different perspective, but that's just how it is. So um, wireless engineers have, as I just mentioned, that they can work in research, in research, doing some fundamental and incremental practical research in developing products in both the hardware, software system, in validation of software, hardware, and different systems as well, and operations and maintenance. So in general, like wireless, I mean, obviously, obviously many of you know that the data communication protocol between a transmitter and receiver are divided into like either like we have options to divide it into 5 layers or 7 layers. And so my point is that the engineers can work in any single layer, and uh, so it's not like entirely specific to any specific layers, because I mean, I was at first I used to think that, okay, if I want to work in the R&D of wireless communications, I only need to focus on the physical layer, something like that. But that's not necessarily true. Research can be done in application layer. Research can be done in the network layer in the industry. So it's not confined to one specific layer. And so um, saying a few words about the research, industrial research in communication fields. I usually, as I just mentioned, I would classify the research in terms of two different techniques. One is the fundamental research, and the goal-oriented and practical research. And so here, for the fundamental research, usually not usually, sometimes a common myth is around us is that the fundamental research can only be conducted in the academic environment, not in industry or like in some other places. But this is not necessarily true for many cases, and wireless communications is an example of one of the examples of these exceptions. Big companies like Intel, like Samsung, Ericsson, Huawei, they continuously hire research engineers to conduct fundamental research works. I know many BUET alumni who are successfully working in the industrial research labs, and they're like doing some amazing jobs there. And yeah, so in addition to the fundamental research, obviously there are like other sort of research which are very practical, and engineers solve some practical problems through innovations, and they always contribute to the standardization activities through their work. So well, let's say for cellular communications, we have 3GPP, the standardization organization for cellular communications, and also for IEEE. So the research engineers who are involved in those kind of research, they always contribute to those standardization activities is solve some practical problems. It's not like that they create the problems and then solve it. They have their problems at hand. They solve they just come up with some sort of like really cool solution techniques. And from the development side, the development engineers, they usually coordinate with the standardization guys, and then they come up with the algorithm or some sort of like solutions that are dedicated for the development of a product. So I myself, let's say, worked as a wireless systems engineer in Intel Corporation and briefly at Oppo US Research. So I worked on the development side. I worked in the development in the physical layer algorithm, especially in the baseband chain. And we had we always had to like communicate with the research engineers who are part of like the standardization teams, and then we had to develop the algorithm for our product. Development does not necessarily is only specific to algorithm development, but the software development, firmware engineers, hardware development, they're all part of development. They work closely to each other in the in industries, and as an outcome, we really see some really cool product. A large number of engineers work in the validation as operations. Engineers continuously validate software, system, hardware, and validations are usually done in multiple stages, like in the component level, in the simulation level. They are done in the lab, and also in the live network. So as a wireless engineer, we also have a big chunk of area where we can contribute we can do our jobs there. And usually debugging follows the validation, and validation engineers need to be really expert in debugging these sort of issues that they face in the lab or a live test. And designing the validation strategies is a really powerful task for a successful production. And at the same time, maintenance and operations, which may be slightly different from the validation, but they are also like they're also like really cool jobs for the real-time engineering, and especially from the network side, from the base station side, from the core network. And usually the validation, there's a joint validation, like I didn't say joint validation. The validation both comes from the semiconductor industry and also from the vendor network industries. So that's something like I just wanted to say that, okay, wireless systems engineers have options to work in different fields or different areas in different roles in the industry. Then I would like to say a few things. I'd like to say a few words to my younger version. If I would find a time machine to travel back to my early 20s, like in my 3-2 or 4-1 days in BUET, and if I would plan to work in the areas of wireless communications, first and foremost, I would make sure that I take these courses in my undergrad and graduate level, no matter what I do my studies. But let's say an undergrad level, I would also obviously want to make sure that I am done. I know the things from analog and digital communications, part of like the communication theory course. I have strong background on digital signal processing. I know computer programming to some extent. I know how to deal with the statistical tools, statistical signal processing, random process, noise, things like that. In the graduate level, obviously the antenna and microwave theory, and then backed up with wireless communication, cellular communication systems, information coding theory, detection estimation theory, data communication, and computer networks. These are like some sort of like essential course that I would obviously make sure that I did them, I finished them, no matter what the grade would be, but I have to make sure that I took them. And based on my research area, then some sort of like optional courses. Let's say that I am working on the artificial intelligence. So it's always good to have some like fundamental background on artificial intelligence. Maybe that may be offered from different department, but that's also cool. Like we know the basics, or maybe the optimization theory. Like when we solve the resource problems, we need to solve some optimization theory, or someone who works in the optical fiber communication, like free space optics, something like that. They need to have some sort of like understanding on how these kind of things go on in the theory. And then I would try to teach myself some tricks. Like, let's say that that's something I actually learned through some hard way, and that's what I just want to share with you guys, just to see that, okay, I mean, like, you also can be benefited by applying some tricks. So if I were like in my early 20s, when I would take all these courses, the first thing that I would like to see myself is I would try to implement the theory in practical systems. Now the question comes that, okay, who is waiting for me with a practical system where I can apply the theory? It's not that easy. So okay, it's not that easy, but what I can do is just I can start myself by writing down a small piece of code in whatever programming language that I am comfortable with. This is one of the easiest ways to do that, and trust me, it works like a magic. I mean, let's say that we are working on the MATLAB, and let's just open an open text file, write some codes that that you just learned. Let's say that you learned how the convolution works. Just write down a small piece of code and see how this convolution works. It will just work like a magic to grasp the main idea. I will never forget those things. And even like say for more complicated scenario, there are a bunch of toolbox out there in the MATLAB, like LT system toolbox, 5G toolbox, wireless LAN toolbox, and trust me, you can just configure E node B or base station. You can configure an UE or like a cell phone with this toolbox. And now some of you guys that can argue that, oh no, we don't want to work with the MATLAB because in industries, many of the industries, maybe small industries, they cannot afford MATLAB. Okay, let's go with some open source tool. Just do these simulations in Python. There are a bunch of libraries available there. NumPy is one of the libraries that can literally do more than 90% of the job of MATLAB. And okay, you don't have the exposure of LT system toolbox. Let's find some open source tool. Let's say SRSLT. You can simply configure eNodeB. You can simply configure UE with this open source tool. So these are like really available things that are here right now, but that was not there when I was in my early 20s. So let's just try to exploit all of them. The second thing is that, like, okay, writing some codes is good thing, but if we can get a chance to get involved with some hands-on project means like we have a goal and we have to maintain the goal, then it would be great. Now the question is, where can I find these projects? Like, do I not need an advisor or some sort of like a help? Yeah, obviously we need, but at the same time, we can just start by ourselves. But how? I mean, should I create my own problem and then solve my own problem, something like that? Yeah, we can do that. We can come up with some really cool research papers. But in order to get our hands dirty, I mean, there are like a lot of open problems out there in the standards, in different blogs, in different hobbyist page. And then let's say that ARRL, amateur radio, ham radio, those are like really cool stuff where you can get your hands dirty. And like there are like a bunch of people um, who have channels in the YouTube, like Dave Kessler from Denver. He works on really cool stuff. There's some other guys out there. They can do a bunch of different things, and we can follow them. We can do our own things, even staying at home. It's not like that we have to be in the lab. We can exploit some software-defined radio. These are not that much expensive, and we can use MATLAB or open source tool like GNU Radio and can do the project and can see. I mean, like, let's say that we can configure one transmitter, one receiver. We can practically, literally can see that, okay, signals are being transmitted, although maybe with some limited configurations. And let's say that we developed something, we developed our resource allocation algorithm. We can readily put our algorithm in those systems and they can work. We can see the end-to-end performance. So this is something that I feel this is really cool stuff that I was at the time, those were not very much available, but right now things are available. It doesn't mean that we have to be physically in some place. We can do all these things staying at home. We can do a bunch of different things. Even I know that for some of the SDRs, they are, if we cannot afford them, but there are some online community, online help where we can just remotely do all these things. Learning tools is always important, especially like when I was working with these two companies, like um, tools. I mean, we don't want to reinvent the wheel. We don't want to research, don't want to do the research to reinvent something that was already there. So let's say that my manager tells me to write down to evaluate the performance for with the deep neural network. I don't have to write down the code from the scratch. Instead, there are a bunch of tools out there. I can exploit them as long as my company allows and there is no issues of no legal issues or something like that. We can do a bunch of different things with these tools. Now you can complain that, okay, where can I get this expertise? There are a bunch of tools out there for online free streaming, free videos. Some of them are paid, and then like Coursera, Udemy, LinkedIn Learning. There are a bunch of courses on TensorFlow. There are a bunch of courses on how we can develop our own deep neural network to get our hands dirty. So we can do that. And at the same time, like someone can say that, okay, following the literature or reading the IEEE papers is not that important, even to work in the industry. So, but they're completely, I would say, from my perspective, they're not necessarily true. I mean, even when we do research, obviously we need to know the latest contributions, latest like outcome. But at the same time, when we work in the industries, we need to know what's going on in the community. Like we need to regularly read the magazine papers, survey papers, and tutorials, transactions. We always need to get in touch with what's going on in the industry. And one thing is that we may sometimes need to know some sort of like interdisciplinary tools. Let's say someone can argue that, okay, we are electrical engineers, maybe we don't need to know the programming, but even if we have some sort of like expertise in one single programming language, it's not that easy, not that difficult to learn some other things. And trust me, some like C++, or C#, Java, that might be too much like front end or like back end oriented. That's a different topic. But if we know them, that helps us doing some like jobs or doing some sort of like projects in practical world, developing some skill sets, let's say in Linux environment, in bash command, learning to use how the open source development boards work. I mean, not by thinking that these boards are only the property of the microcontroller engineers or something like that. So what I wanted to say is that in addition to the courses, if we can apply our theory in practice, practical systems, or even by writing some codes, doing some projects, and then learning some tools, exploiting some freely available resources out there online, and then getting our hands dirty with some interdisciplinary tools, like getting involved with a different programming language, or like knowing something about Linux, knowing something about the hardware, that actually helps a lot to get a good career, to become successful in the long run, not only for the wireless communications, but also for different areas of electrical and computer engineering. So sorry, I most probably talked too much. So that's all for now from me. Thank you. Sajid, sorry, I took a lot of time.
No, thank you so much. First of all, that was a really fantastic presentation, and not only you covered your broad area, and you also spoke specifically regarding how one should prepare on the wireless communication, or how one student can work on open source problems and then work towards the career. Now the floor is actually open for questions, and I see that Pallab Kumar Moitra has asked a question. So Pallab, if you could unmute yourself and ask the question, you can go ahead.
Hello, sir.
Yeah, hi.
Yes.
Okay. So nowadays we see that in our market, I live in Noga district in Bangladesh. There have so many mobile set, like hardware-based mobile set, they sold in market, but their encryption system in software that is so much less. But they connected in SIM connected internet supported SIM. That's I thinking that's 2G preferable set maybe when it's connected in 3G connected internet, the encryption of SIM, that means our fingerprint, like so many things that's affected because the software installment in this set so much lower case, and I think that is difficult to, in our security matter. Sir, I want to know about this effect of in our system.
Oh, okay. Yeah. Thank you so much for this question. So let's say that the security. Okay, fine. Let's say that you were talking about the heads the mobile sets, the cell phone sets that are, let's say, that were originally configured for 2G GSM slash basic CDMA, but let's say that the network has been like upgraded to 3G, and now you're facing some problem like because the encryption is not same, something like that. That's what you asked. Honestly speaking, mm, um, these are very specific to the network service providers and also for the manufacturer of those phone sets. Let's say that usually for, I don't know, but most of the phones, let's say that I purchase an LTE support phone or 4G supportable phone. They are backward compatible. Usually that should not be an issue from the cell phone perspective, from the vendor perspective. And the problem is that they either, first of all, either we may need to contact to the cell phone manufacturing company or the distributor company to see, okay, whether they released some sort of like drivers what is it called, to upgrade their encryption system, and then they are supporting into 3G. My personal opinion would be there should be something available there as a sort of like an what is it called, the software developer, software upgrade, or some sort of like driver that we may need to install, and then it should solve the problem. Should not happen, but if I would be in your case, at first I would definitely contact the distributor company or the cell phone manufacturing company, and not to blame the network right away. Should not be the case. The network service providers, they should satisfy all these corner cases. Does it answer your question, or did I just like talked around and then is it okay? What do you think?
Thank you so much. That was really good. I think Mr. Pallab is muted at the moment. So we still have time for more questions. So if I don't see any more in the chat box, but the audience members, you're welcome to go ahead and ask more questions if you like. So
hello, yeah, Dr. Sajid, I'm Dr. Mohammed Hassan Imam saying.
Yeah, hello.
Hello. Hello, Dr. Imtiaz, how are you?
Assalamu alaikum. Hassan bhai, how are you doing?
Yeah, we are mates in the BUET. How are you? A long time. We do Bangladesh.
Yeah, long time no see. Of course, bhai. Obviously, bhai.
আমরা আসলে একসাথে বুয়েটে ছিলাম, তো we have a lot of long memory, right? So
we have a long memory, and হচ্ছে হাসান ভাই হচ্ছে আমার হচ্ছে যে গুরু, এবং ওনার কাছ থেকে আমি হচ্ছে যে অনেক কিছু শিখেছি. I will stay grateful to him till my last breath. Of course. No, ভাই আপনি আপনার কাছ থেকে অনেক কিছু শিখেছি. Thank you so much.
আমি আসলে এই ওয়েবিনারটা আসছি জাস্ট তোমার নাম দেখে, সত্যি কথা, just want to talk to you.
Thank you so much. Thank you so much.
I'm very happy to see you there, and mashallah, you're now US. So you left the job in Intel, right?
Ji bhai, I left the job. The job in Intel. I mean, like, there was no specific reason. I just wanted to work in the academia. Working in Intel was a really masterpiece for me. I really enjoyed working in Intel, but I just wanted to work in the academia as something I got, and then I said that, okay, I would like to avail this opportunity.
Okay, I just have one question to know, because you were in on that side. We heard that there were some challenges of the 5G implementation, right? There's some controversial issues, like the countries like US and other developed countries, they are also arguing like whether it can be implemented in the developed or developing countries. So what's your comment on that? Like আমি যেটা বলতে যাচ্ছি, কিছু controversial issue নিয়ে আসলে আমরা দেখতেছি যে 5G আসলে আমাদের দেশে আসবে কিনা বা আসলেও, what are the challenging, do you think, from your experience?
হ্যাঁ ভাই, থ্যাংক ইউ সো মাচ ভাই ফর দিস কোয়েশ্চেন। ভাইয়া একটু কি কাইন্ডলি হচ্ছে যে একটু হাইলাইট করবেন যে কোন পার্সপেক্টিভ থেকে চ্যালেঞ্জিং গুলো, মানে হচ্ছে
যেমন
যে
আমি হ্যাঁ যেটা হচ্ছে লাইক
ইয়েতে
এনভায়রনমেন্টাল
ইলেকট্রোম্যাগনেটিক,
ইমপ্যাক্ট,
ইয়া ওকে।
হ্যাঁ এটা যদি আমি একটু বলো।
আচ্ছা আচ্ছা ভাইয়া, ওভারঅল হচ্ছে এইগুলো মানে যেটা হয় যে যদি হচ্ছে যে নেটওয়ার্ক সাইড থেকে আমরা দেখি যে অনেকেই হচ্ছে যে করছে যে ওকে আমরা we are going towards a higher range of the carrier frequency gigahertz range, and that can put like lot of detrimental impact on the environment. বাট এট দ্য সেম টাইম হচ্ছে যে ভাই রিসার্চও চলছে বেশ কিছু, যেগুলো হচ্ছে মানে যতটা মানে সেফ ওয়েতে জিনিসটা করা যায়। আর আরেকটা জিনিস হচ্ছে ভাই মানে এখানে যে মিলিমিটার ফর দ্য টাইমিং লেটস সে যে এখন যে অবস্থায় হচ্ছে আমরা 5G তে হচ্ছে ডিপ্লয় করতে চাচ্ছি, সেটা হচ্ছে যে মেইন network main what is it called main anchor will be LTE, still sub 6 gigahertz, মানে gigahertz range 6 gigahertz এর নিচে, but for higher gigahertz range, let's say for 26 gigahertz or 52 gigahertz range of carrier wave, ওগুলো অনেক ক্ষেত্রেই কিছু কিছু ক্ষেত্রে স্পেসিফাইড যে একটা স্মল সেলে হচ্ছে ডিপ্লয় করব বা কিছু ইয়েতে ডিপ্লয় করব। সো মানে হ্যাঁ মেবি হচ্ছে যে আমাদের হচ্ছে মানে পুরো বড় একটা ম্যাক্রো সেলে হচ্ছে আমরা 32 গিগাহার্টজ এর একটা ডেটা ট্রান্সমিশন হচ্ছে হয়তো দিতে পারবো না, ছোট ছোট জায়গায় দিতে পারবো। তো সেই ক্ষেত্রে হয়তো কোএক্সিস্টেন্সের জন্য না ওই ধরনের প্রবলেম যদি কোনো কোনো জায়গায় থাকে, ওইগুলো সামহাও একটু হয়তো হচ্ছে যে মানে রিভিজিট করা যাবে, হয়তো হচ্ছে সলিউশন গুলো দেওয়া যাবে। এটা হচ্ছে যে আমার মনে হয়। আর যেটা হয় যে ডেন্সলি পপুলেটেড এলাকার রেসপেক্টে যদি আমরা চিন্তা করি যে মানে ইউরোপিয়ান কিছু কিছু ডেন্সলি পপুলেটেড জায়গা, সেখানে কিছু ফিল্ড টেস্ট হচ্ছে, সেখানে বেশ কিছু জায়গায় হচ্ছে এই প্রবলেম গুলো হচ্ছে সর্ট আউট করা হচ্ছে। সো ফার অসুবিধা হওয়া উচিত না।
Okay, thank you very much, and very nice presentation, Imtiaz. Very nice presentation.
Thank you so much, bhai.
Sorry, I called Imtiaz. Sorry for that.
No. No, bhai. Thank you so much, bhai, for attending. I really appreciate. Thank you so much, bhai.
And thank you, Dr. Sajid, for attending this nice webinar. I thanks all the attendees here. Okay, thank you. Take care, huh? Best of luck.
Thank you.
Thank you. কোন ব্যাচ by the way?
আমি ছিলাম 98, BUET 98 ব্যাচ। 98 ইমতিয়াজ ছিল, হ্যাঁ 2 বছর।
2000 batch 98. Thank you.
Okay, thank you very much to all of you. Thank you.
Thank you.
Thank you so much, and we still have more time for questions and comments. So if anyone wants to add anything or ask anything to Dr. Ahmed, you can go ahead.
Assalamu alaikum, sir.
ওয়ালাইকুম আসসালাম।
আমি জাহাঙ্গীর হোসাইন, তো ব্যাচেলর করতেছি মালয়েশিয়াতে। বাংলায় কথা বলি তাই না, সবচেয়ে ভালো হবে।
অবশ্যই।
হ্যাঁ, তো আসলে আমি 1 বছর আগে ওয়্যারলেস কমিউনিকেশন মানে শেষ করছি, তো আমার কিছু কনফিউশন আছে অ্যাকচুয়ালি হাউ দে উইল ক্লাসিফাই দ্য 5G 4G ইভেন দ্য 6G।
আচ্ছা ক্লাসিফিকেশন আসলে আসবে হচ্ছে মানে এটা জেনারেশনের ভিত্তিতে, তো মানে হচ্ছে যে সেকেন্ড জেনারেশন, থার্ড জেনারেশন, ফোর্থ জেনারেশন, and in every single generation we have a set of requirements. We have a set of requirements in terms of like data rate or coverage area. So let's say that when we moved from second generation to third generation, in the second generation we had I mean like limited data rate, and then we wanted to increase the data rate from kilobits per second to some sort of like a megabits per second, and then we had to find out some new techniques. Let's say the second generation হয়তো GSM ছিল, basic CDMA ছিল, then we went for a wideband CDMA, something like that for 3G, or like from 3G to 4G we exploited like OFDM, orthogonal frequency division multiplexing. Usually from one generation to another generation there is a paradigm shift, যে GSM থেকে CDMA GSM থেকে হচ্ছে যে wideband CDMA হয়েছে, and then like wideband CDMA থেকে OFDM technique আমরা ইউজ করছি, and they drastically increased the data rate and some other performance features. যখন 4G থেকে 5G তে হচ্ছে যে আমরা ইনক্রিজ করছি, তখন 5G তে আমাদের দেখা গেল যে cellular communication they try to make some other application areas under their control. যে আচ্ছা ঠিক আছে যে IoT, at first people started using IoT with them, like let's say a different bunch of like mesh network like Wi-Fi, like Bluetooth, something like that, LoRa, and there are a bunch of like other networks was there. Standardization was there. Then in LTE হঠাৎ করে হচ্ছে যে 3G দেখলো যে হ্যাঁ, okay, we need to put our fair share on LTE. They started doing the narrowband IoT, which is a small subset of LTE, and then they jumped into the LTE market, and then from LTE থেকে হঠাৎ মনে হলো যে আচ্ছা ঠিক আছে, IoT has to be in a broader scale, and there is something knocking on the door, which is ultra reliable and low latency communications, autonomous driving, remote surgery, things like that. So they want to bring those the application areas under their umbrella, and then 5G তে দেখা গেল যে okay, we have different scale of of performance or application areas. 5G তে it's not like we will have the increased data rate, but we have some diversified area of IoT. We will have diversified area of autonomous driving, remote like surgery, as I just mentioned, and then that's why দেখা গেল যে তখন আমাদের আরেকটা প্যারাডাইম শিফট করতে হলো যে আচ্ছা ওএফডিএম ছিল, এখন ওএফডিএম থেকে কি আমরা আরেক কিছু কি করব, ওএফডিএম থেকে অন্য কিছু ওএফডিএম পাওয়া যায়নি, কিন্তু দেখা গেছে যে ক্যারিয়ার ওয়েভটাকে আমরা আমরা ইলেকট্রোম্যাগনেটিক স্পেকট্রামে যে রেঞ্জে আমরা হচ্ছে করতাম, ট্রান্সমিশন করতাম, আমরা হাই রেঞ্জে ট্রান্সমিশন করার চেষ্টা করি। তো কোশ্চেন হচ্ছে হাই রেঞ্জে মানে হাই ক্যারিয়ার ওয়েভ ট্রান্সমিশন আগে কেন পসিবল ছিল না? আগে পসিবল ছিল না বিকজ অফ আওয়ার লাইক দ্য ইন্ডাস্ট্রিয়াল, আই মিন দ্য ইলেকট্রনিক্স ইন্ডাস্ট্রি, PLSI was not that like fast. When they came to our I mean, like when they started contributing towards this thing, then we said that okay, now we can apply many antennas. We can put all the antenna elements into some given space. Let's apply the massive MIMO, things like that, and then serve those kind of purpose. So I would say যে একটা জেনারেশন থেকে আরেকটা জেনারেশনে অবভিয়াসলি অনেক অনেক প্যারাডাইম শিফট করে, বাট ইট ডাজন্ট মিন যে ওই শিফটটা করেই আমরা ওখানে স্টপ করে থাকি। 3GPP তে অলওয়েজ উই হ্যাভ সাম কন্টিনিউয়াস ইমপ্রুভমেন্ট, এভরিথিং, I mean in every 3 to 4 in every 3 months some new techniques come, people meet and then they come up with some broad new topic. But one generation one একটা জেনারেশন থেকে আরেকটা জেনারেশনের এই শিফট গুলো আসে হচ্ছে প্যারাডাইম শিফট। 1G থেকে 2G থেকে 3G তে যেরকম GSM থেকে ওয়াইড ব্যান্ড CDMA, 3G থেকে হচ্ছে 4G তে হচ্ছে OFDM টেকনিক ইউজ করা হলো, 4G থেকে 5G তে ওকে আমরা OFDM টেকনিক থেকে আর কিছু না ইউজ করে মেবি আমরা হচ্ছে অন্য কিছু করার চেষ্টা করি, ম্যাসিভ মাইমো নিয়ে আসি। তারপর অন্য আরো হচ্ছে যে লাইক নিউমেরোলজি চেঞ্জ করি, যেগুলো হয়তো এখানে হচ্ছে করিনি, কিন্তু এভাবে আসে। 6G তে দেখা যাচ্ছে যে ওকে maybe AI will be I mean, AI artificial intelligence will be much more than what we have right now in 5G or what we are envisioning for 5G. So some drastical things will happen, and this will make the change from one generation to another generation based on the requirement of the customers.
Thank you, sir.
Thank you.
Thank you very much. So if there is any other questions and comments, you can unmute yourself and then communicate. And while we also want to take a group photo with Dr. Imtiaz Ahmed, our speaker, and all the guests. So if you are comfortable, you're invited to please turn on your webcam so that we can take a screenshot and virtual photograph. So আপনারা যারা আছেন আপনাদের ওয়েবক্যাম অন করতে পারেন, আমরা একটা সবাই মিলে ছবি তুলব, এবং সেটা করার সময় আমি একটু আমার স্ক্রিনটা কুইকলি শেয়ার করতে চাই। So আমরা প্রথমত so first of all, we're really glad that we could host one of our former chair of young professionals today, and not only he was a active volunteer of IEEE, he was an active researcher and extremely active faculty member at Bangladesh, and now he went back to industry and then again came back to academia. And we were extremely lucky and honored to have Dr. Imtiaz Ahmed as a resource speaker today. So this is a virtual token of appreciation presented to Dr. Imtiaz Ahmed for being a speaker at our Meet the Young Professional webinar and giving his talk today. So I really am glad and grateful that you consented and to come here and gave this wonderful talk.
Sajid, thank you so much. Thanks a lot for having me. And it's really be an honor for me to get a chance to talk to you guys. And if you have any questions, feel free to reach out to me. And thanks a lot. Thank you so much.
Thank you. And now I'm going to go ahead and take the virtual photo, the group photo. So if you want, you can turn on your webcams. So with this, I would like to thank everyone for coming here and joining our virtual event today. And if you want, you can give a event feedback, and we would be, if you're interested, we would send you a certificate of participation. Also, we would take permission of Dr. Imtiaz Ahmed and show him the recording. If he's okay, we would then share the recording in our YouTube channel. But first we would get his permission and then share it. So please.
Yeah, sure. Of course. And if you want, then I can also share my presentation slides. That's perfect from my side.
Oh, thank you so much. So please have a look at our YouTube channel where we would be posting it. So with this, I would like to thank everyone and then conclude today's session. Thank you so much for joining us.
Thank you.
Yeah, thank you very much. Thank you, Imtiaz. Allah
Thank you.
Allah
Hafiz. Assalamu alaikum.
Assalamu alaikum.